Okay.
Next slide, please.
So I will start with the introduction. It is for me a great pleasure to introduce Fabian Schneider, the speaker of today's talk. Fabian got his PhD in 2015 in Bonn, Germany. And after that, he was a Hinz Research Fellow at the University of Oxford between 2015 and 2018. After that, a Gliese Fellow at the University of Heidelberg. And just recently, he was designated a junior group leader at the Heidelberg Institute for Theoretical Studies. He was a recipient of a European Research Council grant to start his own junior group. He was also recently a recipient of the Ludwig Biermann Award of the German Astronomical Society. So it is for us a great honor to have you here today with us. And Fabian will be talking about neutron star and black hole formation in binary stars.
So Gloria, thanks a lot. I heard half of it because I got disconnected in the meantime. This is really annoying and I'm so sorry for that.
So just a comment, Felipe, can you stop recording and can you begin recording again? So we take off from the recording, from the video, the discussion about the meteor that we had at the beginning. Felipe, I think I can do it.
Hi, everyone. Sorry for being a bit late.
Hi, Diego. So please, Javier.
Yeah, I'll give it another try. And I really do hope that I'm not losing connection again. So can you see my slides at the moment?
Yes.
Okay, fantastic. That's great. I'm just trying to get the Zoom window here also so I can see actually when I'm losing my connection again. Okay. All right. So thanks a lot for having me. It is a great pleasure actually to share some of our recent work with you. And as we've already discussed previously, if you have any questions, please just do interrupt and ask anytime. That was absolutely fine with me. So I thought it would be great to talk about how neutron stars and black holes form in binary star systems. And I hope that this is of interest to actually a larger group here in the audience. And before I start with that, I would like to share my excitement actually with massive stars and stars in general. And I think we're having actually a common ground here. So as you all know, the stars are our basic building blocks of the visible universe. And it's always great to look back essentially of what they have done throughout the cosmic evolution. So if you think about the early Big Bang and then the evolution towards today, this is today here on the right-hand side. And then you can look into different things, for example, how stars have produced all the chemical elements, in particular heavier than helium, of course. And here's a little periodic table where you can sort of try to grasp actually which element has been produced in what kind of star and maybe in Big Bang nucleosynthesis or maybe via some cosmic rays or so. And I think it's always great to look into, for example, some oxygen or maybe even carbon and silicon, which is the stuff that we are made of. And you'll see that, for example, the oxygen mostly comes from high mass stars, in fact. And then if you think about other stellar objects and other stellar sources, you know there are many iconic astronomical objects. So I'm just depicting some planetary nebulae here for you. And depending on how time goes on, maybe we can even talk a bit more about those. But what I'm really interested in are massive stars. And these massive stars are considered cosmic powerhouses. And so what do I mean by that? If you again go back into history of our own universe, you know in the beginning, after the cosmic microwave background froze out, the universe was pretty much pitch black and pitch dark. And then you form the very first stars and galaxies, and they then suddenly start to reionize this universe. And these are sort of these massive stars that we're talking about today. Also, if you look into galaxies nowadays and also across cosmic evolution, then the stellar feedback drives their evolution. So here's one of my favorite pictures where you see this reddish outflow from this galaxy, and this is supposed to be driven by supernova feedback, for example. And speaking of supernovae, of course, you can observe such spectacular transients essentially across cosmic time, and then also probe cosmic evolution. And once these supernovae go off, they leave behind some of the most interesting objects, I guess, or some objects with extreme physics, and that these guys shall be the focus of my talk today, so black holes and also neutron stars. But I would like to talk about binary stars. You might wonder, okay, so what's the connection now from binary stars to these black holes and neutron stars? And that is simply because most massive stars are in binaries. They're observationally found in binaries, and that has huge consequences, as you all know. So I do want to show you a little animation, and I really hope it comes across Zoom now. So we have a pair of two massive stars. And as always, the somewhat more massive star, which is this whitish object here, it expands first. And then at some point, its outer layers will be gravitationally attracted stronger by the companion than by its own gravity. And then you have a phase of mass transfer, when now this whitish object is losing its envelope, and the envelope is slowly and steadily being transferred onto the object, the companion. And this companion here, you can see it also accretes some angular momentum even in this little animation, so it's now oblate. And in the end here, you get a supernova from a star in a moment that has lost essentially its outer envelope. But also, in fact, the other star has now accreted some mass, and so is also maybe not a normal and usual star as you might otherwise think. So why do we care about these binary stars? And probably you are all familiar with this kind of diagram that I took from Max Mohs and Di Stefano's paper. And I'm showing to you now the fraction of different stellar systems as a function of the primary mass of the most massive star in this system. In red, you have a single star fraction, and then you have binaries in green, triple stars in blue, and also quadruple stars are shown here. So for example, what I always like to look into is just a solar-like star at 1 solar masses or so. You can see that about, let's say, 50-50 or 50% of stars are single, and the other half is essentially in binary star systems. And if you then go up the mass and go into the high mass domain, you see essentially all of these massive stars, they are born in binary stars or higher order multiple systems. And that has, of course, consequences, as I was already mentioning. So you can try to guesstimate pretty much what is the fraction now of stars that are going to interact. By interaction, I mean exchange mass, for example, in this way that was depicted in this animation. And then you see also that this fraction steadily increases, now goes up with primary mass, and about at a primary mass of 5 solar masses or so, you have roughly that half of stars will do something with their binary companion in terms of mass exchange in their life. And if you then come back and think about supernovae and stuff, those are, of course, only from the most massive stars that we have. And so from this diagram, you immediately conclude that if you observe any supernova in the universe, then it has a very high chance that a binary product, meaning a star that has accreted or lost mass, has been exploding here. And that is sort of the topic of today's talk. And I would like to start essentially again with this picture that I had in this animation, but now in still images. So I just want to talk you through some of these binary mass exchanges and binary mass exchanges. So I would like to start out essentially on the 0H main sequence. So we do see two.
May I ask a question?
Yes, please.
Yeah, Danny Page. When you say binary, but this means what fraction of them will be actually interacting?
Yes, so the fraction essentially of the interacting stars, that's sort of the guesstimate that you can get. So if you have, for example, a stellar system where the most massive star has 5 solar masses, and I'm saying stellar multiple system because it could also be a triple or a quadruple system, but then anyhow, mostly the closest binary pair is sort of the one that is going to interact first. If you add 5 solar masses and then you look into such systems, then about half of them are going to exchange mass with a companion. And it is almost 100% more or less, actually, if you go into stars beyond, let's say, 10, 20 solar masses or so. So for the guys that explode in a supernova, that's sort of the relevant part. It's almost all, I would say.
Okay.
But
in the left panel, this was no consideration of interaction or no. It was just binary triple.
Absolutely. So on the left-hand side, this is only the config or the kind of incidence rates of the different systems. But of course, the orbits, for example, they can be so wide that the stars will never be able to exchange mass by binary mass transfer.
Okay.
And this information has been factored in then on the right-hand side in this diagram.
Okay, good. Thank you.
I have a question too.
Mhm,
Why
yeah.
why is that? Why low mass stars are mostly isolated and massive stars are mostly in binaries?
That is an excellent question, and I really wish I would have an answer to this.
Okay. So we don't know.
It's a
Doesn't it
very-
have to do with the age? I mean, low mass stars, when you see them, they have been around for such a long time that they may have just separated from their cluster. And unless they were very close binaries to begin with, is that a possibility?
I suspect this is a part maybe of an explanation, but I'm not sure that is the explanation to explain the entire thing well. So,
Okay.
I mean, observational biases will certainly sort of be in that game, but such a drastic difference, I don't know. I guess we have to wait for some people to build better star formation models, and then hopefully we'll know better in the future.
Okay, thank you.
All right. I would like to show you just a couple of sketches, more or less, to get you a bit more familiar with sort of what this binary mass exchange is and what it can do in principle. So I would like to first of all repeat more or less what you already saw in the little animation. So we have two massive stars here on the 0H main sequence. And then also in this video, we saw the more massive star here is going to evolve first, and then it expands. And at some point it hits its critical Roche radius, its Roche volume limit, and then mass is transferred onto the companion. And after this mass transfer phase, essentially what you're left with is the remaining core of that star. And this envelope here that was on top is gone. It has now been accreted onto the companion. And this star that has lost its envelope can then, of course, explode in a supernova. And this is essentially how far we got in this video. But of course, there's much more evolution thereafter. And this evolution is going to be really interesting. So for example, what can happen? Is the following, that now, of course, also the other star that has accreted now a bit of mass, it is also going to evolve. It might slightly increase its radius, and it will have a strong wind. And this wind material, for example, could be accreted onto this compact object here. And this compact object would now be a neutron star or a black hole, doesn't matter so much. And then maybe you find a system of a high mass X-ray binary. So that is sort of an evolutionary channel that we think high mass X-ray binaries could come from. This star here can expand actually further, and what might happen is that it expands to such a large radius that it can completely engulf now this compact object into its envelope. And this is then a phase that we call common envelope phase. So a common envelope means we have now the compact object and also the core of the star, and they are engulfed by a common envelope that is represented by this hydrogen envelope of this high mass star here. And in this common envelope phase, this is also going to be terribly complicated. And I could probably also actually give a whole talk on that now, but that's not going to be the focus here. But what can happen is that this envelope is simply ejected. The orbit of this binary star system then shrinks, and you use this orbital energy that is released to unbind and eject the envelope. And what you're left with then is this compact object here and the core of this primary star, or of the initially secondary star and now the primary star. And also that star can, of course, then explode. And if this explosion is such that the stellar system is still bound, then what you might finally have is a double neutron star binary system. And of course, such a double neutron star binary system might emit gravitational wave emission, and well, it will emit gravitational wave emission, and this gravitational wave emission might be sufficient also to then lead to a merger of the double neutron star system. And that is where our gravitational wave events, the LIGO events, ultimately come from. And here I hypothesize that you form a black hole as a result of a merger of two neutron stars. But this is only one evolutionary sequence, and things can be completely different. So let's start out just with a slightly, let's say, less massive companion here in the beginning, or alternatively, we put the orbit into somewhat larger scales. And what can then happen is the following. Again, you have this primary star here, this blue guy expands, it starts a mass transfer phase, but this mass transfer phase can now turn out to be unstable. And such an unstable mass transfer phase, that's what we already saw here in this other step in the first evolutionary sequence, that could again lead to a common envelope phase. And now we have this companion star here that's engulfed again into this envelope. The envelope might be ejected again by the release of gravitational binary orbital energy. And what you're left with then is again 2 stars. And the first star here, this helium star, then might also explode in a supernova. And you have a system formed of a neutron star or a black hole plus this companion. And the companion again is going to expand, as was the case before. And here now, because the star is of lower mass, then you might have actually a low mass X-ray binary system where the X-rays are fed by direct mass transfer from this lower mass companion onto this compact object. The ultimate fate of such a system would then rather be that you have a millisecond pulsar here, a rejuvenated, a spun up neutron star, and the companion here, this white dwarf, just remains and is of course also a system that you observe quite frequently in our own galaxy and elsewhere.
Fabian, could you define a little bit better what you meant by unstable mass transfer, that very first step there?
Yeah, all right. So what I was envisioning here is the following situation, that the orbit is so wide that when this mass transfer is initiated, that this star here that expanded has developed a deep convective envelope. And stars with a deep convective envelope, they have the funny property that if you start to remove mass here from the envelope and you accrete onto the companion, then the envelope expands actually. And so this is then ultimately leading into a runaway situation where you keep transferring envelope material, the star gets bigger, then you accrete even more mass onto the companion, the star gets even bigger, and at some point the companion is literally just engulfed into this envelope. So that is what I meant with dynamical, unstable kind of situation from this binary mass transfer.
Okay, thank you.
Okay. And something similar can also happen if you imagine that the binary star system here in the beginning was maybe much closer. Yeah. And in such a situation, what simply can happen is that both stars are going to evolve. And because the binary was already so close, then both stars can actually get physically into contact configuration. So the surfaces literally touch, and we have mass transfer essentially from one star to the other and also from the other to the first star. And that is a contact phase that ultimately might lead into the merger of both stars. And the merger itself is, of course, also interesting. I hope I can show you a couple of simulations on that in a moment. And here we are going to hypothesize, or I'm going to argue, that you might form then actually a highly magnetized star that might produce a magnetar in the end when it explodes in the supernova. So a magnetar being just a highly magnetic magnetized neutron star. So that's sort of the zoo of binary evolution in a nutshell, I would say. And there are many, many details here that we could probably talk about for a long, long time. But I would like to show you a quite instructive video here. And this is a starburst star cluster, and we're looking into the Hertzsprung-Russell diagram. And this is an initial starburst with 100% binaries. The color bar here tells you a bit about the rotational velocity of stars at the surface. And I'm going to play this animation again, just for you to follow it. So we have here the stars on the main sequence, and you see the development of the main sequence turn off when the stars evolve to the red and become red supergiants. Then you see all these guys that are going to pop up here. And these are the products of this binary mass exchange. So these are classical blue straggler stars that are a result of all this kind of mass transfer that was ongoing in this previous description. And if you were now to sort of integrate over the entire Milky Way galaxy just to see how many of these guys would you expect to find, and then you can come up with the following numbers. The biggest chunk of stars that you're going to observe are in fact binary stars where the mass transfer has not been happening yet, but they are going to transfer mass in the future. Then about maybe 20% or so are true single stars, and the rest, which makes up, let's say, roughly 30% or so, these will be already your binary products. And this is true if you do this exercise in massive stars, sort of O-type stars. Yeah, so reminder again, if you look into O-type stars in the own Milky Way, And if you integrate over the entire star formation history of our Milky Way galaxy, then you'll find that about a third of all stars are expected to be products of such binary mass exchange situations. And for example, here the expectation is that about 8%, or let's say around 10%, are merger stars or merged stars in the O-type regime. There's really another interesting consequence of all this binary mass exchange, and I would like to briefly mention this here. And this has to do with the cosmic reionization that I mentioned in the beginning. You know, these massive stars, they are hot, which is great. So that means they're pouring out ionizing radiation, and they're luminous. So these massive stars can easily be 1 million times as brighter than our own sun. And in particular, if you remove now the hydrogen envelope of such guys, they become even hotter. And so they emit even more ionizing radiation. And people have tried to figure out actually how much do these massive stars, but also these stars that lost their envelope, contribute to the cosmic hydrogen 1 ionization. And so this is a diagram that I found quite interesting from Ylva Röttberg's work from 2020. This is a function of redshift, so you can see essentially how much in this toy model. So I should really stress this is a toy model, but still I think it's quite instructive here. It tells you how much AGN feedback is contributing to hydrogen ionization, how much the stripped stars contribute, and also the massive stars. And you can also just sort of try to integrate this up to a hydrogen reionization, which here happens about at a redshift of 6.5. And you'll see the massive stars and also the stripped stars, they are mostly responsible probably for ionizing hydrogen in the universe. So I found this a really interesting result that they had. And you can also look further into the literature. I just wanted to briefly quote a work by Rostal from 2018. So they took one of their galaxy cosmological structure formation simulations, put in binaries, which they took from the B-path models from J.J. Eldridge and Elizabeth Stanway. And what you can see is that the hydrogen reionization actually proceeds faster. And so it might, with binary stars, already be done about 1 redshift earlier than if you only had single stars. So I found this really interesting also. And maybe for people here in the room that work a bit on escape fractions of ionizing radiation from star-forming regions and galaxies, there's also some interesting work here by Secunda, for example, from 2020. And they show you roughly what the escape fraction in ionizing photons is. And they have a default model, which is just a starburst 99 model. But then these binary stars, they can, for example, produce runaway OB-type objects from a supernova kick. And they will then add even more ionizing radiation because these guys can now travel large distances in the galaxy and then emit their ionizing photons in regions where they can more easily escape, maybe. There's a contribution of these strip stars that I just mentioned. And that helps because these strip stars, they live longer ultimately. And the same actually applies also to these blue stragglers that we saw here. So each of these factors is actually increasing the escape fraction, plus you're pouring in even more ionizing radiation. So I really like these ideas and thought it was worthwhile sharing with you. But I would like to come back now to today's topic. And this is the landscape of things that I just showed to you. So I would like to briefly talk a bit about how now this binary mass exchange, and in particular, if a star loses its envelope, how that affects what kind of compact object you get. And then I would like to show you some results that we got on how stars might merge and what might come out of that. But I don't think probably that I have time to talk a bit more about the come envelope phase, but let's see how far we get here. All right, so let's jump into our strip stars. And I have to start with this slide, although I know it's now outdated, because last week there was a publication by the gravitational wave teams with their third catalog. So this catalog is even larger than what you're seeing now. On sort of the y-axis here, you do see the masses of compact objects in solar masses. So this is the stellar graveyard, as they called it. And you have different systems in here. You have in this yellow colors down between masses of 1 and 2. These are the neutron stars that have been measured and observed in the Milky Way galaxy mostly. And most of these measurements have been made, for example, in double neutron star binary star systems or neutron star plus white dwarf systems and so on. Yeah, so in binary stars. Then you have this violet purple color. These are the X-ray binaries that we can observe in our own galaxy. And you see sort of how their masses look like. So here these are high mass, mostly high mass X-ray binaries. And well, Actually, there are only now X-ray binaries shown that have a black hole companion, or tentatively a black hole companion. And then also on top, you've got the gravitational wave events. And there's a hell lot of information in this, already just in this graveyard. And I just want to point out a couple of interesting aspects. So first of all, you probably noticed that there appears to be a dearth or a gap between the neutron star masses and the black hole masses. So that's interesting, maybe to realize, and then also trying to understand why that actually is. And maybe you also saw that essentially in our own galaxy, in the X-ray binaries, you have hardly found, actually we have not found any black hole that is more massive than about 20 solar masses. Whereas in the gravitational wave business, you do find plenty of them, right? So that's also another curious aspect, and I hope I'm going to explain to you in a moment why that is the case. And what I'm not going to talk to you about today is the tentative gap, another mass gap, the second upper mass gap that is being produced by so-called pair-instability supernovae. I'll leave that to someone else to talk about this in the future in your seminar. So I would like to highlight now in this figure, and I'm going to have another slide on this, that if you make mass measurements and obtain masses of these compact objects, then you make measurements in systems, in binary star systems, where essentially all of them had a mass exchange history at some point. So they have transferred mass from one star to the other in the evolution. And just to highlight maybe this once more, so I just went back to this picture here showing you the different evolutionary sequences and the evolutionary directions, and also the stellar graveyard, and just want to highlight essentially from what kind of objects do you measure the neutron star the masses of compact objects. For example, here down in the neutron star regime, yeah, you can measure it in double neutron star systems, and if you look back into the history of such a star, there was a lot of mass exchange happening while the stars were still alive, and then we are measuring the masses. Same, of course, if you measure it, for example, from a neutron star that is in a system with a white dwarf, then again, the entire evolution that formed this neutron star is subject to binary mass exchange. Same for the X-ray binaries, obviously, so have it then the evolutionary sequence here. And also, of course, if you think about the compact object mergers, ultimately the blue data points on this diagram. So these stars within the channel of isolated binary star evolution, they all had an interesting history of mass transfer. And so we need to understand what has happened and how that maybe has changed a star and then its explosion and also compact object properties. For that, we have to go a bit back in understanding what is happening in stars, and also in understanding that this mass exchange episodes, they can occur in different phases of a star's life. And I'm only going to talk to you now about stars that have lost their envelopes in a binary mass transfer event. And this mass transfer event can essentially occur at any moment in the star's life. So I'm showing you the radius evolution of a initially 13 solar mass star. It only increases its radius a bit while it is burning hydrogen in its center. And then it is crossing the Hertzsprung-Russell diagram through the Hertzsprung gap, becoming a giant star. And then finally also undergoing core helium burning here, and then also all the other burning stages thereafter. And so you can capture it and remove its envelope in different phases. For example, you can already do this while the star is still burning hydrogen in the center. So I'm trying to make little sketches here so that you can get an idea of how the interior structure looks like. So we now have a core here, a convective core that is slowly burning hydrogen into helium. And then we remove this outer layer. Or you can have something that we call case B mass transfer. And that would be only after the star has burned hydrogen completely into helium. And then you have a shell still of hydrogen burning surrounding this core. And then this is the envelope, the hydrogen-rich envelope that is lost in a binary mass transfer event. And you see that the core structure is already quite different after such a mass transfer phase. And probably you can imagine that this might make a difference. If you go even further into what we then call case C mass transfer, this only occurs once the star has also finished core helium burning. And so that means the star has established a carbon and oxygen core, which is surrounded by a helium burning shell and a hydrogen burning shell. And then you only remove sort of the outer layer. And maybe already from these little graphs, you can guess that in this late phase, if you then only remove the hydrogen layer, maybe this actually doesn't do too much
Se nos quedó congelado.
Sí.
Oh, so that probably means I was
Fabian?
not. Yes,
I think we lost the last minute. Can you go back?
the last minute. Oh,
No, less.
25, maybe? 25?
okay.
The CO core. You were at the CO
Okay, you
core.
saw the CO core. That's
We
great.
lost
So
you in case C.
Oh, you lost me in case C. I'm so sorry. So I was about to say, so case C mass transfer, it means you have burned all the helium into carbon and oxygen. And then around your carbon oxygen core, you have a helium burning layer and also a hydrogen burning layer here out. And then you only remove the hydrogen layer that is still on top. And maybe you can already guess from this little sketch here that if you then remove the hydrogen layer, maybe not much is going to happen to the inner core of the star because it has already established this structure. So what you have left actually then after core helium burning has finished is a carbon and oxygen core. Yeah? All the helium is converted into carbon and oxygen. And I just want to show you sort of the properties of such cores at exactly this moment when helium burning is over. So here on the y-axis, you have the mass fraction of carbon that is left in this core. And on the x-axis, I'm showing you the entire carbon and oxygen core mass. If you want to convert that into the initial masses of stars, I'm also giving you some numbers here on the top. And this is for the single stars. And you can see the single stars have a nice sequence in this diagram. If you had an initially less massive star, it finishes core helium burning with a higher carbon core mass fraction. And if the star was a bit more massive, then it has fewer carbon. And these two parameters are of utmost importance now if you want to know what happens at core collapse and how this core evolves further. Because the next burning sequence is carbon burning. And I guess you can already see that a massive star has pretty less, just a bit of carbon left. And so this burning phase will be completely different than maybe if you look into an initially less massive star that has much more carbon still to burn. Yeah, so these two parameters are sometimes considered to be biparametric kind of configuration to explain later on what happens in late burning stages. So I would like to show you now how these different strip stars look like in this diagram. Maybe the easiest first. By definition, Kc mass transfer has to give exactly the same result because Kc mass transfer, as described previously, only occurs after core helium burning. So here we have identical two lines. So that's good. But with case A and B mass transfer, sort of when the star loses its hydrogen layer on the main sequence and just thereafter, then these strip stars, they form a complete separate contribution here in this diagram. Yeah, so we have a displaced sequence, and this stripped binary sequence now produces or leaves more carbon in their centers after core helium exhaustion. So that's the first message I would want to point you at. And that is that the cores of these strip stars, they are going to evolve differently than those of single stars. And to understand maybe on how this core evolution then is different at the final phases when the star is about to collapse, I'm showing you again here on the x-axis the very same carbon and oxygen core mass. But on the y-axis, I'm showing you what we call the compactness parameter of the ion core or of the entire interior core of the star. And the compactness is a really useful but simple quantity. And you'd simply define the compactness at a certain mass coordinate, m, and then you divide by the radius of this core at this very mass coordinate in units of 1,000 kilometers. Yeah? So it's just a measure of how dense, if you like, or how compact this core really is. And you see that the single star sequence that we've computed here, it has given rise, for example, to what we have called a compactness peak here at some point, and then you have an entire compactness landscape. And if you want to have a critical value for supernova explosion or just implosion, then people have used, for example, a value of 0.42. And here you would maybe see that everything below this line might explode in a supernova, produce maybe a neutron star, and everything that has reached a higher compactness is going to form a black hole. So maybe then the stars that are here in this compactness peak are going to produce a black hole rather than a neutron star. And now you can compare actually to this stripped binary sequence. So the Kc is again kind of boring, but actually also nice to see that they behave pretty much like genuine single stars. But the other case A and B strip stars, they behave completely differently. So their sequence or the landscape of this compactness landscape is quite similar, but it appears to be shifted to somewhat higher carbon-oxygen core masses. So you can see this maybe here from the compactness peak, it is now at a higher carbon-oxygen core mass. But more importantly, I think I would like to emphasize this flank here on the right-hand side, where the single stars reach much higher compactness values already at smaller carbon-oxygen core masses. Yeah, so the second message here is indeed the stripped stars have a different pre-supernova core structure compared now to the single stars, and that's an important message. So we also wanted to know, of course, now what does it mean for the supernova explosion? And then we took a parametric supernova explosion model here by Bernhard Müller and tried to guesstimate a bit more quantitatively what comes out of these sequences. I'm showing you now, as a function of the initial masses of stars, what is the neutron star mass down here, and what is the black hole mass of different stars that are being formed, the complete objects that are being formed. I want to highlight a couple of aspects. First of all, this is our compactness peak that are already motivated. That probably gives rise to black holes and no longer neutron stars. And as expected, it's now shifted from about 22 solar masses or so to almost 30 solar masses in the strip stars. That's the first interesting aspect that we found here. And what is even more relevant maybe is the following: the neutron star formation itself in single stars and KC systems is such that any star that is less massive than 35 solar masses can actually produce a neutron star, roughly here, what I'm just indicating. And every star that was initially more massive at solar metallicity, I should say, forms a black hole in these models. In the case A and B strip stars, however, this transition, as you can see here, only occurs about at a mass of 70 solar masses. So in these strip stars, if you start out initially with a 70 solar mass star, then that is sort of the boundary between neutron star and black hole formation. You can also see this gap that I was just mentioning previously between the neutron star and black hole masses. And here in our model, this gap actually is between 2 and 9 solar masses. So you probably noticed that the observed gap is about, the DART has a magnitude between 2 and 5 solar masses or so. And we think that the width, more or less, of this gap is closely connected to how much fallback actually occurs in a supernova explosion at all. So if you imagine, for example, we have more supernova fallback, or actually fallback at all in a supernova, then you can, of course, narrow down this gap by converting some of the black hole, the neutron stars maybe into black holes, and then you can narrow down this gap a bit. So it's also an interesting, I think, realization from this work. And the other one that I also highlighted previously is the maximum black hole mass that we can find in an X-ray binary. And remember, in an X-ray binary, the compact object has formed from a star that lost its hydrogen envelope in a mass transfer event. And here in our models, we do not find a single star, not an object, not a binary strip star, that produces a black hole beyond 20 solar masses. And this was quite beautiful because it just after we published that paper, there was a revision of the black hole mass in Cygnus X1 from 15 to 21 solar masses. So in our paper, we are still arguing and discussing, okay, what could maybe cause this discrepancy of 20 versus 15 solar masses or so. But then this mass has actually been revised, and of course, we are much happier now. But we shouldn't be surprised, I guess, if this mass is revised once more. But still, the idea, I think, holds. The reason why in our Milky Way galaxy we do not observe more massive black holes is simply because the star that has produced this black hole has been stripped of its envelope previously in the evolution, and that limits, and quite naturally, then the maximum black hole mass that we can get. Maybe I'll leave out the implications for what this might mean for gravitational wave merger rates, just maybe very quickly. If you simply consider now that many of the stripped stars rather produce neutron stars and not black holes, that means you will get fewer black holes from binary star populations. And this in turn, of course, is going to reduce quite a bit maybe the black hole merger rates and also black hole neutron star merger rates that people would get if they, for example, use this quite famous Chris Fryer's 2012 supernova model. But that's just as an aside. If you want to talk more about it, we can do it maybe later. I do want to highlight a few more interesting aspects of these stripped stars. And the first one is that we also find that they have somewhat higher explosion energies. They're systematically higher by about 0.2 beta. So here's a histogram of our explosion energies that we get from the single stars and also from the different stripped objects. And most interesting also, the stripped stars in our models, they produce somewhat more nickel. The difference doesn't seem to be terribly large. How far did I actually? How far did I get with you?
Like less than a minute.
All right, so I guess you did see the explosion energies, but probably not so much the nickel masses. Is that correct?
Yeah.
Yes.
Okay. Okay. So just maybe I can do this quicker. The bottom line is the following: the stripped stars, they have high explosion. All right, I was again gone. That's really ridiculous today. So you see more nickel in type 1b C supernovae, sort of supernovae from stars that don't have a hydrogen envelope. And the equivalent of hydrogen-rich supernovae, type 2p supernovae, they actually show less nickel. And so we think that exactly this difference in the progenitor stars could actually cause this observed difference here. There's also something interesting maybe for people that are more interested in kicks, and that is with the higher explosion energies and also the somewhat smaller neutron star and black hole masses, we also expect that the kicks from a stripped star are larger, and the sort of systematic shift that we find in our models is of the order of 100 kilometers per second. So it's not dramatic if you consider that the average kick is anyhow of the order of 300 kilometers per second, but I think it's still noteworthy at this moment. Okay, so I would like now to stop talking about stripped stars and supernovae from stripped stars, but instead briefly jump into stellar mergers. So if you remember, recall from the beginning, this was sort of this landscape or the zoo of different binary interactions that are possible. And now I would like sort of to talk about this phase here where two stars get into contact, ultimately merge together, and would like to show you a couple of interesting highlights. I cannot do this before I have before flagging up some interesting work from other people. I do get another interesting message from Zoom telling me that you only now can see my screen. Is that correct?
No, we have been seeing it.
Okay, good. Thank you, Gloria. So this is some work that Stephen Justin did in 2014. And what they did is they tried to see if you merge two stars, in which part of the Hertzsprung-Russell diagram are they going to explode? And here they find, for example, that if you merge a 25 and a 19 solar mass star, this guy is going to explode somewhere as a, let's call it a blue, yellowish supergiant star. And that is, of course, interesting, because you know that a supernova 1987A, the progenitor here was a blue supergiant with an effective temperature of the order of 60,000 Kelvin and luminosity of about 5. And also it is quite unusual because it has a bipolar and a ring nebula here. So this is an artist impression down here, and this is a real picture. And I'm pretty sure people here are familiar with work by Morris and also Podsadlovsky, where they try to explain this funny star, this progenitor star, by being a remnant of a merger product. And more recently also, Yosuke Hirai, he wrote a beautiful paper about how maybe Eta Carina also could simply be a merged star, and maybe also this eruption that we have seen from Eta Carina, maybe that was actually due to a merger of two stars. So it's also an interesting prospect.
Do you know how much mass do you have in the ejecta from the merger?
In Eta Carina or in
the 1987A?
That's a good question. No, I don't know. But my guesstimate would be, so if this is, so they considered a relatively late case C merger in their work. And so I suspect then that that in total you might be ejecting about 10% maybe of the total mass at the point of a merger. And so if we're talking about let's say 20-ish stars. So that could be a few solar masses that were
Wow.
ejected.
Okay, a lot of mass. Yeah.
So there could be a lot, exactly. But of course, this mass or the ejection would happen prior to the supernova. So there might be actually quite a delay between ejecting the mass and then suddenly or finally the supernova going off. So in Eta Carina, the ejected mass that people infer is much higher. So it's 10, 20 solar masses or so. But also the stars involved are probably of the order of 100 solar masses or so. But it's really interesting work. I recommend having a look, and also in some previous work by Nathan Smith. Yeah. Anyhow, but that's not really what I would like to talk to you about. I would rather like to talk to you about how merging can maybe even produce strong magnetic fields. And our work was actually motivated by a funny observed star called Tau Scorpii. And this is a magnetic star, one of these magnetic massive stars. And in this massive star business, we have that about 10% of them show a strong and a large scale surface magnetic field. And the quest is still out to identify where this magnetic field comes from. On top, Tau Sco appears to be a blue straggler in its Upper Scorpius association. So we thought, okay, we have to try to see if we can find a model of two stars that we can merge together and then finally get an object that resembles the appearance of Tau Sco. So what we did is we took a 9 and an 8 solar mass star on the main sequence, and then we merged them using the moving mesh code AREPO. And maybe some people know AREPO, that is usually used for cosmological structure formations. For example, the Illustris simulations, they were run with the AREPO code. But you can also use it for stellar astrophysics, as we're showing here, for example. So I do want to show you now on the left-hand side the density in the equatorial plane, and also on the right-hand side the absolute magnetic field strength. So I'm showing the videos, but I have some still images in a moment, just in case they're not playing well. So you have this nice peanut system of two contact or deep contact binary stars. And in this contact binary configuration, you do have accretion streams from both stars to each other. And in these accretion streams, you start to amplify the magnetic field, the sealed magnetic field that we put into the stars. And this amplification works out exponentially. And we have also identified the agent that is mainly responsible for this amplification, which is the so-called magnetorotational instability. And maybe some people rather know it from accretion disks, where it provides the effective turbulent viscosity actually to allow for fast accretion processes, for example, in X-ray binaries, in cataclysmic variables, in star formation, maybe even in AGNs and so on and so forth. But it seems that the same instability can also operate during a stellar merger and then helps or mainly actually amplifies the magnetic fields in our cases. So as I promised, I have a few still images because I think it's easier to see over Zoom now. I would like you to point or sort of to pay attention to the first panels here. And so this is the magnetic field, again in the equatorial plane, and you can see both stars here. And in particular, in the very beginning, what we have here is a phase where mass is being transferred from one star here onto the other, and this mass accretion stream, it scratches, if you like, on the surface of the other star. And then also even it comes back to the primary star from where it has originated originally. And then also it starts to scratch here on that surface. And in these accretion streams, this is where we find the magnetorotational instability to kick in first. Yeah, and you can see that in these regions in the magnetic field is amplified in the beginning quite strongly. And then you have also ultimately the merging phase itself, where the two cores of the stars are finally tidally disrupted, and then they form a new core of the star. And I've magnified this here further because in this configuration, when the two surfaces of the two cores or the interfaces actually finally merge, you can also find beautiful Kelvin-Helmholtz instabilities that, of course, can also then contribute to the further magnetic field amplification here. So that was quite surprising and interesting for us, of course, to see that this idea actually did work out. And I do want to highlight another interesting aspect of these merged stars. And
Sorry,
that is,
Fabian?
yes.
What was the seed, the magnetic seed, initially of the?
So we put a dipolar magnetic field in the beginning, and it had a dipolar strength at the pole of 10 to the minus 6 Gauss. So it was nothing. Yeah? And then it's exponentially amplified over, I don't know, 10, 12 orders of magnitude in magnetic energy until we reached, and finally here, maybe I should have mentioned this, in the center, in these whitish regions, magnetic field strengths of up to 10 to the 6th Gauss, maybe even a bit further.
Wow.
Was quite.
Is that the time scale? Is that the actual time scale, 5 days that it amplifies?
That's right, exactly. That's the time scale. Absolutely correct. So time scale for amplification here, due to the MRI, is of the order of days, actually a fraction of a day, even in some of these layers here. Yeah. Exactly. So we have defined time 0 as a point when finally sort of the two cores here are tidally disrupted, and then they sort of come together and form a new core of the star. That's also quite nice to see actually that in the beginning here, the cores are completely unmagnetized, but later on, this magnetization is then also taking place in the core itself, and magnetic field amplification also, but you also have adaptive motions, fluid motions here, that then sort of slowly bring stuff, magnetized material also in the center. The other aspect that I wanted to highlight is the following. In a binary star system, before they merge, you have a lot of angular momentum, of course. And this angular momentum has to go somewhere. And what it does is it forms a massive torus surrounding just a merged object. And this is maybe best depicted here on the bottom line, so where you're looking edge on into this merger remnant. So in the beginning, you have this nice peanut shape, and then stars are going to merge. And you see here, you have a big torus. It's sort of a disk-like torus. So the rotational velocity is Keplerian-like, not exactly Keplerian, because we are also pressure supported in this disk. And in the central region, you have a almost spherically symmetric remnant. This torus is really massive. So you have about 3 solar masses in this part of this merged, shredded star that you're left with in the end. And that, of course, poses a big question: and how does such a star or such a remnant actually evolve further? And you have to make quite some assumptions to get to this. And I would briefly like to highlight how we imagine how the further evolution of such a star could go. And for that, I'm showing you an Hertzsprung-Russell diagram now, but this is now only a comparison single star model, so that you can see how this merged star actually compares later on. The color of our merger remnant will be depicted here. The rotational velocity on the surface is in color. But this is the single star that has the same mass as our merger remnant. And the merger remnant itself takes this route through the Hertzsprung-Russell diagram. So it looks a bit complicated. Let me talk you through it. So we start out here essentially in this peanut configuration, contact configuration. And then on a time scale of order 10 days or so, the merger itself happens. And you form this object here, spherically symmetric star in the center that has this massive torus. And from there, essentially, you have to argue a bit of what happens to this torus. And we think that most of the torus is accreted rather rapidly onto the star. And then it forms this puffed up kind of giant here, not exactly that hot anymore, also a bit cooler. But this star, of course, has been heavily perturbed. And in particular, in its outer layers, there's energy that has been deposited, and this energy needs to now leave the star. And what it does is simply it expands the star up to a maximum luminosity here, and this expansion occurs on a time scale of a few years, and then it radiates away much of its energy that has been deposited there, for example, from this binary orbital energy. And then from this point on, the star contracts and gets back into equilibrium, and then finally is again on the main sequence and can continue its core hydrogen burning phase. And this is the phase in which we observe tau score. And at this moment here, we do actually in our model have a star that resembles tau score quite remarkably. It resembles it in terms of its effective temperature. And this was a one-time guess. Yeah? So we only tried one model and tried to guesstimate in the beginning, okay, what kind of stars do we need to merge, and what is the evolutionary sequence or the evolutionary stage that we need these stars to be in to later on get out tau score. So there's no fine-tuning really here. So we got tau score remarkably well. The luminosity is maybe a bit higher than what tau score has, so we would need to go a bit lower in masses with our stars. But also the surface gravity is quite similar. The magnetic field strength, if you do magnetic flux freezing from this magnetized shredded star, is perfectly in range for this typical magnetic massive stars that are observed. And another really intriguing aspect of our model is that while the star, of course, after it has merged, rotates critically, so high or bright colors here, high rotation velocities, in this evolution up to maximum expansion, it spins up. And when the star finally contracts back to the main sequence, it spins down. Yeah? So this is completely counterintuitive probably to what you think about ice skaters and conservation of angular momentum, but it has to do with a funny moment of inertia that the star has, and the interior structure has to relax to its final configuration, and this changes the momentum of inertia, and then at the end actually the star rotates rather slowly. You can also see that the further evolution of this merged star is pretty much the same as the single star, and that is you had main sequence stars that are merging and they fully rejuvenated. The only difference being this merger remnant has now a higher helium abundance in the envelope. This higher helium abundance makes it just a bit more luminous. But otherwise, we will get a type 2 supernova here. But then maybe this type 2 supernova is in a star that is highly magnetized. And that is where we then hypothesize that maybe this is a formation channel for a magnetar. But I should really point out there are many open questions still to this entire evolutionary sequence and scenario. And if you want to know more, we can talk about this in a moment.
Sorry, I do want to know a bit more, Philip. So what the orange line in the initial, what was the 0H main sequence mass of that?
So that's 16.9. That's pretty much what we had after the merger.
Okay, so and the mass of what you obtained there in your stage 4, what is the mass of that object, and what is the magnetic field that it ends up evolving a lot like that 17 isolated
Yes. Exactly. So our merger remnant, when it arrives down here, it has the same total mass as this initially 16.9 solar mass star. So both have 16.9 solar masses roughly. So that's how we constructed this orange kind of single star model.
Okay.
The magnetic field from magnetic flux freezing, if we assume that the entire magnetic flux that we got after merging can be conserved, will be of the order of a few kilogauss.
Okay.
Tau SCO itself has a surface magnetic field. Well, you see here, this is a reconstruction of its surface magnetic field. And so how do you now define its magnetic field strength? Usually people define it then as some dipolar component or longitudinal component. And then they come up with values of the order of a few hundred Gauss. But that puts Tau SCO exactly into this ballpark of magnetic stars, where you have a few hundred Gauss up to the most magnetic star has 24 kilogauss surface magnetic field. And our merged remnant here is pretty much in the same ballpark as these magnetic massive stars. Okay. And Tau SCO also is actually a slowly rotating star, as would this, our default model would also be a slowly rotating star. But there are really uncertainties associated to this rotational velocity, I should say. And at the moment, it seems plausible to us, but maybe if you learn a bit more, particularly about this phase, how this torus accretes onto the remnant, that is, I think, what we think what sets the final rotation of the star here once it's back on the main sequence. But that phase is also probably the most unknown in this entire scenario. So we need to learn more about this phase to then also say definitely something about the final rotation of the star here.
Thank you.
I would like to maybe just hypothesize a bit what can happen in the end. What kind of star do we get out? What kind of compact remnant? And then I'm going to finish for today. And the only argument again that we can make is pretty much about magnetic flux freezing at this moment, because following the entire magnetic field evolution in a star is utterly complicated. Plus, we only have one-dimensional stellar models at our disposal at the moment. So this is pretty much almost, I wouldn't say impossible, but it's challenging to have a proper magnetic field evolution. So what we did instead is the following. We were saying, considering now, so this is our merged remnant, just how it looks afterwards, and the color is the magnetic field strength again, as before. And we're also trying to indicate a bit the orientation or the geometry of this magnetic field. Yeah? So you can even see, while the MRI, the magnetic rotation instability, produces only small-scale local magnetic fields, ultimately, because of these advective motions, you have, of course, a strong toroidal field component, as you can maybe already guess from these streamlines in this plot. But also, if you look edge on onto the same thing, you can also see that there are large-scale dipolar components even emerging from this remnant star. It's quite remarkable, actually. And so what we did is the following. We played a simple game. We were looking into the innermost 1.5 solar masses of our star, and we are measuring essentially the magnetic flux in this region. And then we're saying, okay, take this material, and if you were to take a teaspoonful of material from this merged remnant at this moment, you would probably gather about 10 grams. But of course, when this central region finally becomes a neutron star, then the density is going to go up enormously, and you go from 10 grams up to 10 to the 9 tons if you were again to take a teaspoonful of material. So what it just means is if there was magnetic flux that is frozen into the structure and you don't lose much of that, then you can reach, of course, via this compression of this inner region, magnetic field strength of up to 10 to the 16 Gauss. So this is even larger by about a factor of 10 compared to what we observe in the most magnetic magnetars. And also, the prediction from this model would be that this neutron star remnant here is rather slowly rotating. So you have a slowly rotating, highly magnetized, maybe inner core of a massive star at core collapse here in this situation. And an interesting comparison is maybe if you look into the magnetar formation rate in our galaxy. This has been guesstimated by Keen and Kramer in 2008 here, for example. They find that about 0.3 magnetars are formed per century in the Milky Way galaxy. You can contrast that to the galactic supernova rate of the order of 2 per century. That is from radioactive aluminum decay. And then you come up with an order of magnitude that about 15%, or let's say again 10-ish% of supernovae form a magnetar. And just remember, this is the same order of magnitude as you observe in these magnetic massive stars. And it's also the same order of magnitude as we expect, for example, for the incidence rates of mergers among O-type stars. Yeah, so it's of course just circumstantial evidence, but it's great to see at least that there is no obvious contradiction to this scenario. I do want to mention, of course, that these highly magnetic neutron stars in the Milky Way galaxy here, they will not produce a superluminous supernova, just in case you might now get get your thoughts going. However, these stars, of course, might be responsible for short gamma repeaters and also fast radio bursts and so on and so forth. So there are many interesting transients linked to magnetars that might actually form from such a scenario. Okay, so I think I'm going to stop here with my summary. And I thank you very much for being with me and having me with you. And again, I'm really sorry that my internet connection here was so unstable today that I dropped out a couple of times. I still hope that you could get maybe some of the main ideas of that talk, and I would be happy to have more discussion and more questions from your side. So thank you very much.
Thank you. So are there any questions?
Well, I have several questions.
Go ahead, please.
Maybe I can just start the discussion off. And I'm curious because, Fabian, you showed this plot of initial mass and CO or helium core mass. Mm-hmm. And of course, the mass of the core is going to depend on the mixing efficiency. So I am assuming that you're using normal, relatively standard mixing efficiencies, which then leads me to the question of what has happened to the scenario of chemically homogeneous evolution. Has this scenario now, is this no longer as popular? Or could you say something about the mixing efficiencies?
Yeah. So we were considering in this exercise when we're talking about the stripped supernovae about the simplest models that you can make, and they're non-rotating. So the only mixing efficiencies that we had to deal with here in this scenario is essentially convection, and that we know roughly how efficient it is. If you, of course, want to maybe play the game and go into chemically homogeneous evolution, that would be also really interesting to see, for example, what kind of compactnesses and cores do you produce from such a channel. But then you would need to do two things. First of all, you have to have a star that really rotates rapidly in the beginning. And also you have to make sure that you can maintain this fast rotation throughout the life of a star. And that means you have to make sure that the star cannot lose much mass. And that, for example, you can do by placing it at a really low metallicity, so that the stellar winds, for example, are really weak. But also in this classical stripping of the hydrogen envelope, of course, that would also remove a lot of angular momentum, and maybe that then kills off the chemically homogeneous evolution. But what you might be more interesting is to look at is not the star that has lost the hydrogen envelope, but maybe the companion that has accreted this hydrogen envelope. Because if you accrete now material from a star, then you also accrete not only mass, but angular momentum. And so this accretor, that could be spun up then by this accretion process to relatively high velocities. And that could be a way then also to trigger this chemically homogeneous evolutionary pathways. So if you're interested in that, I suggest have a look into some papers that Matteo Cantiello wrote with Seung-Chul Yoon, for example. They considered a couple of these scenarios, but the chemically homogeneous evolution is by far not out of the game. In particular, if you think about massive black hole mergers from gravitational wave sources. But these are literally not, well, we did not consider them in our scenarios here.
But is it not true that the mixing efficiencies are very uncertain and that you don't necessarily need rapid rotation to have high mixing efficiencies? I mean, those are the current models, but is it not possible that in the binary, because of the asynchronous rotation, your mixing efficiency could be higher?
Yeah, absolutely right.
But your results, the fact that you're finding consistency with the stripped stars would point towards that scenario not being present, not being active, right? Am I right about that, or am I not seeing something?
No, it could both occur at the very same time. But the kind of additional mixing that you're talking about, that would be relatively small, for example. Well, okay, let me go back one step. So the systems that we are considering, where you have binary mass transfer and you can strip off the hydrogen envelope of one of the two stars, that is something that works in most binary star systems that are initially so far apart that you do not get this chemically homogeneous evolution by tidal locking. I think that's the scenario that you're currently in. If you're in this tidally locked situation, then you trigger, exactly as you say, chemically homogeneous evolution, but then the stars stay compact and they might not really go into a phase where they transfer mass at all. So they keep all the mass to themselves. And so you avoid the envelope removal. But that's not the binary stars that we were looking into here when we are considering situations by construction that lose the envelope.
Okay.
You can have both, but this channel was just not considered by us.
Okay, thank you.
Welcome. So I see another hand up here.
Diego, do you have a question?
Yeah, I have a rather naive question. So when you put like slide 13, when you put your three possible pathways, you put there 20% go towards the right and then 25 to the close contact phase. Based on, or how did you sort of determine those numbers, like with?
Yeah, good, excellent question. So these numbers come out of so-called population synthesis models.
Yeah. Okay.
And they are really, really simple. So they are guesstimates for orders of magnitudes. And for example, how you can guesstimate the contact phase situation. It's also quite easy, actually. So what you need to know is what is the distribution of the periods or orbital periods of binary star systems. And for the mass ratios, you're probably good off assuming that you have a uniform mass ratio distribution. So every mass ratio is equally possible or equally likely in a binary star system. And then these contact phases, we roughly have an idea in which part of the binary parameter space they actually do occur. And they occur in systems, for example, on the main sequence. If you're talking about main sequence stars that start mass transfer, then if they start the mass transfer at a mass ratio that is smaller than about 0.5, then they go into contact. That's something that we know relatively well. And so then you can do the math, and you can simply add up all the systems that might go into such a contact phase as a main sequence stars that start to interact.
Okay.
And then you have a somewhat less certain contribution, and that is from so-called case B mass transfer phase. So when the primary star that initiates mass transfer has already left the main sequence. And there, this critical mass ratio is a bit different and less certain, I would say. But what people usually use is, for example, that this is of the order of a quarter or so. So if the mass ratio is smaller than 0.25, let's say, then you assume they're going into contact phase. And if you then simply integrate the binary parameter space with such a simple kind of guesstimate, then you come up with numbers like 25%.
Okay.
And it's even funny if you play with these critical mass ratios a bit. You can maybe pick not 0.25, but take 0.3, 0.4, or whatever. The order of magnitude in this case of the order of, let's say, 25%, or maybe 10%, or maybe even 30, 40%, this is going to stay. So it's always going to be roughly of that order of magnitude. And same works then for this unstable mass transfer phase that goes into Karma envelope evolution.
Okay.
Do a similar exercise.
Okay. Thanks.
You're welcome.
Okay, other questions? Enrique?
Yes, hi. It's been messy with the lost connections, and then I was doing two things at once, so I couldn't follow all the stuff you mentioned, Fabian, which is really interesting. So Zoom dropped me out when you were about to talk about Cygnus X1, which was one of the interesting things to me, so I didn't know what you said there. But also, so you were mentioning a lot of KC mass transfer. And so one of the things I remember from my papers on my PhD between 2006 and 2010 was that for KC mass transfer, you need stars which have not lost the outer envelope. And for that, you usually need to reduce, you need a reduced metallicity and or reduced winds from the typical models. So it's not common to have KC mass transfer, at least not in our galaxy from what I remember. So do you get any of these things happening in your models in our galaxy, or is it only for lower metallicity galaxies?
Yep, great question. So we do get a few models in here at solar metallicity that will go into KC mass transfer. And the limiting factor, more or less, for solar metallicity is a bit the initial mass of a star. Because maybe I go back actually to the figure where I'm showing you. Here we are. So this is the radius evolution of a 13 solar mass star.
Mm-hmm.
You see, the definition of KC is that the star has to expand to a larger radius after cohelium burning.
Right.
And not all stars, as you rightly say, will actually do so. So if you, for example, if I were to show the same diagram with a, let's say, 20 solar mass star, then the maximum radius the star reaches is here at this point. Can you, actually, I can maybe get my pointer back. So it's going to be at this point here.
Mm-hmm.
And so such a star will then never, ever experience KC mass transfer if it is a solar metallicity star. So that's completely correct. And in our models here, the limiting mass is, I think, about 15 solar masses. So if you have initially a star that was a bit more massive than that, then actually it would not expand to radii that are larger than here at the tip of the giant branch or before cohelium burning. And so we would not expect KC to happen in these situations, but only in these somewhat lower mass, initially lower mass stars, we actually do also get some KC contribution. And let me go back again to the compact remnant masses here. So we did try to actually indicate this in this plot, but I don't think it comes across Zoom. So we have these triangles here for KC, and we're plotting the let's say, the real KC system that can absolutely do this as the full kind of triangles. And then we have also lighter yellowish triangles here. Those are systems that will probably never experience true KC mass transfer in an isolated binary star system. I mean, you can still, of course, trigger that maybe in a triple star or some other configurations, but not in a vanilla type binary star. So you're completely right. If you go to lower metallicities, as you say, then probably the parameter space for KC is going to be much, much larger. So there's a lot of work that has been done exactly on this in this direction. People that come to my mind is now, if you look into Jakob Klensky's work, for example, former PhD student in Nijmegen, and well, some of his colleagues also, I think also in Amsterdam, Selma's group did work a bit on such questions. So yeah, it's quite interesting. So you can expect more KC at lower metallicities, as you said.
Right.
But KC is boring for in our case, because if you remove the envelope, at least here in the models, then the core evolves pretty much just like that of a single star.
Yes, but it's well, at least in our models, it was important because you want to have the largest possible core and still be able to have a common envelope very late in the evolution, so you can bring the companion star closer, then synchronize, and that will give you back rotation, and that allows you to produce collapsars.
Mm-hmm. Yeah, that's right.
Right.
I think Gloria has another question, right?
Yes, I have a question coming back to your magnetar scenario. Maybe more than a question, it's a comment. There is a Wolf-Rayet binary system called CQ-CEP that has very massive objects. It's eclipsing, and it has an orbital period of 1.6 days. So it is nearly in contact. And because it is an eclipsing system, the eclipses have allowed a determination of the p dots, the orbital period changes over time. And it seems as if the orbital period sometimes goes faster and sometimes goes slower, which leads to the conclusion that sometimes one star is transferring mass to the other one and then vice versa. So you have a situation where you have this back and forth mass transfer. So I was wondering, how long before this system goes into the scenario where you predict a merger and a magnetar formation?
That is a great question. So this ping pong mass transfer that you described, it can go on for a long, long time, I suspect. And you said these are two Wolf-Rayet stars?
The one component has a Wolf-Rayet spectrum. I think it's WN7, one of these hydrogen-rich Wolf-Rayet stars. And they're both very massive. And people have, for a long time, avoided it because apparently there is a second binary. It's a quadruple system, so nobody wants to mess with it. It's too complicated. But the binary itself, the Wolf-Rayet binary itself, is potentially an interesting candidate to follow and see what will it evolve into a merger?
Yes, absolutely, yeah. So the question is going to be whether the stars do expand in their further evolution. And the time scale of this expansion, if it happens, so if they're massive enough, and for example, they always stay compact and they lose their outer envelopes maybe, and then sort of evolve towards the helium main sequence, sort of to hotter temperatures, then their radii are not going to increase much, right? And so then maybe they can avoid a contact phase at all. So that's possible. But if they, for example, then actually do decide that they want to expand a bit more than what they are, at what radii they are at the moment, of course, then I think you can maybe get them into a contact configuration. But that will depend on many, many things. So it's just talking into the blue now, at least from my side. But yeah, would be interesting to see. I mean, you can probably try to model it to some extent. With mass transfer also playing a role, I guess the mass ratio you said is they're quite similar. even in the contact phase itself, the system can be stable for a long, long time. So there are many also massive contact binary stars that are known. We have some, for example, in Large Magellan Clouds, and there's also the lower mass equivalent, so-called WUMA systems. And they must be stable for a long, long time. So that you can just put these two stars into contact, and contact does not necessarily mean that they're going to merge anytime soon. So you then still need another agent or another kind of mechanism that finally merges them together. So one way would be if the stars then expand that far that they lose mass via the outer Lagrangian points.
Okay.
And you have a mechanism that would drain orbital angular momentum quite efficiently, and then you can trigger the merger or take the classical Darwin instability. But that probably requires to have a different mass ratio than you have now. So you probably need one star that is much more massive than the other, and then you can maybe trigger Darwin instability, and then you get a dynamical merger. Or you can,
Okay.
So-
Because that was my question. Does the fact that a star is in contact mean that it will eventually merge? And if so, why don't we see so many more mergers? But I guess the answer is the one you just said. You need a third agent to produce the merger. Okay, very good. Thank you so much.
Contact is not sufficient, at least not in the beginning.
Right, thank you.
Welcome.
Okay, I don't see more questions. So